Hello everyone. Let's start today with something interesting. Have you ever drawn a circle and thought, how do we differentiate it? The equation of a circle, x squared plus y squared equals a squared, is not easy to differentiate directly with respect to x. But if we use a parameter, say x equals a cos t and y equals a sin t, suddenly the problem becomes simple. This is the power of parametric form. Parametric representation allows us to describe curves where x and y are expressed in terms of another variable, usually denoted t. Differentiation then becomes possible through this parameter. That's why parametric differentiation is not just theoretical, it's widely applied in geometry and physics, wherever curves and motions are involved. Now let's see the basic formula. Suppose x equals f of t and y equals g of t. Then, the derivative dy by dx is obtained as dy by dt divided by dx by dt. Formula: dy by dx equals g dash of t divided by f dash of t, provided dx by dt is not equal to 0. This comes directly from the chain rule. Since dy by dx equals dy by dt multiplied by dt by dx, we simplify it to dy by dt divided by dx by dt. Let's take an example, x equals cos t and y equals sin t. Then dy by dx equals derivative of sin t with respect to t, which is cos t, divided by derivative of cos t with respect to t, which is minus sin t. So dy by dx equals cos t divided by minus sin t, which is minus cot t. That's how smoothly this formula works. Moving ahead, what if we want the second derivative in parametric form? The rule is d squared y by dx squared equals derivative with respect to t of dy by dx divided by dx by dt. Formula: d squared y by dx squared equals bracket d by dt of dy by dx close divided by dx by dt. This method requires both dy by dt and dx by dt. For example, consider a circle again. X equals a cos t, y equals a sin t. We already know dy by dx equals minus cot t, differentiating minus cot t with respect to t, and dividing by dx by dt, we arrive at the second derivative, which can be expressed as -1 divided by a squared sin cubed t. Higher order derivatives can be found by repeating the same process. Let us now interpret this geometrically. Parametric differentiation is extremely useful for finding slopes and tangents of curves given in parametric form. Take again the circle x equals a cos t, y equals a sin t. The slope of the tangent is dy by dx equals minus cot t. At t equals 45 degrees, that is pi by 4, the slope is minus 1. That means the tangent at this point makes an angle of 135 degrees with the positive x-axis. With parametric form, we don't need to eliminate t to get y in terms of x. Instead, we directly use the parameter to calculate the slope or tangent. Now let's connect it to physics. Parametric equations are everywhere in mechanics. If a particle moves in a plane, its position at time t can be written as x of t and y of t. The slope of the path is dy by dx, which equals dy by dt divided by dx by dt. Here dx by dt and dy by dt are the velocity components along the x-axis and y-axis. So the slope of the trajectory is simply the ratio of these components. For example, in projectile motion, we have x equals ut cos theta and y equals ut sin theta minus 1 by 2 gt squared. Differentiating with respect to t, we find the slope of the path at any point. This gives us the angle of the projectile at that instant. Let's solve a detailed example. Suppose x equals a cos cube t and y equals a sin cube t. Step 1. dx by dt equals negative 3 a cos squared t sin t. Step 2. dy by dt equals 3 a sin squared t cos t. Step 3. dy by dx equals dy by dt divided by dx by dt. Substituting, we get 3 a sin squared t cos t divided by negative 3 a cos squared t sin t. Simplify the terms, and dy by dx becomes minus tan t. This example shows how parametric differentiation handles even complicated curves with ease. Let's quickly revise what we've learned about derivatives of functions in parametric form. We began with the idea that many curves are best represented using a parameter. We then derived the formula dy by dx equals dy by dt divided by dx by dt directly from the chain rule. Next, we extended it to higher-order derivatives like d squared y by dx squared, which we found by differentiating dy by dx with respect to t and dividing by dx by dt. We also interpreted this geometrically for circles and applied it in physics for projectile motion. Finally, we solved a worked example that demonstrated the method. I hope now you clearly understand how parametric differentiation simplifies the study of curves and motion. See you in the next topic, where we'll continue exploring the power of differentiation.